Daniel, and we'll talk about how to test configuration as code written in general purpose programming language, I would say.
Cool. Can we mirror that somehow? I guess it's the staple of the day that everyone has problems with mirroring. Does anybody know the shortcut to mirror? Filmmakers?
Wait, it's under display. Huh? You're in the wrong. Display. Yeah, it's under display.
Yes, I don't have a cursor on it. There it is.
X1.
Command F1.
Command F1.
Command F1.
F1 you need to put the function in.
Beautiful. Okay, sorry for that. Here we go. Great, amazing. Yeah, welcome everyone. I'm Daniel, and this is Create for Speed Comprehensive Infrastructure as Code Testing. This is joint work with David, who's sitting there, and with our supervisor, Guido, who's sitting back there. Well, you all know this news, you all know outages, they are annoying, they're expensive, they happen to the best ones, and especially in the first session, I think David and Corinna had very detailed stories on how things can go horribly wrong. And as we especially at this workshop know, but also through various studies in industry and academia, is a lot of these outages are caused by configuration. Yeah, so this is an uptime study that showed that 40% of the outages they looked at was configuration caused actually, and not by the software. And this is a paper from 2016 that found 600 big outages, which were basically caused by configuration. So if we want to get our systems not to have big outages, we need to actually look at the configuration of these systems. And today we don't do that manually anymore. A lot of that is automated in infrastructure as code. So to get our configuration right, we should look at our infrastructure as code programs that we actually write. And today we looked a lot at how to get languages now for these configurations. We take another look on it. We now don't try to make languages for the configuration. We just try to use programming languages and write actual programs which then express this configuration. And that kind of technology we call programming languages infrastructure as code. And it's today already production ready, available in tools like Pulumi, AWS CDK. There's meanwhile also a CDK for Terraform, and we have our own small solution which is called Muse. Yeah, and in these infrastructure as code solutions, you actually write real programs in general purpose programming languages like Python or TypeScript. And these infrastructure as code programs are real software. So we would think like you can use all the tooling, all the technology, all the software engineering best practices that we have, know, and love. And if we talk about quality, one of them would be clearly testing, right? So if we know testing for software, this is now software, let's just do that testing. Well, there's a problem, and that's what I mainly want to talk about today. Testing these programs is a bit different from systems that we know. And after I hopefully was able to demonstrate you that this is indeed different and the challenge, I want to talk about our solution to it, which is automated configuration testing as an abstract framework, and then our instantiation of it for Pulumi TypeScript, which we call ProTI. So let's get started with a small example. we want to develop now a small program that shall be a static website that is hosted in an AWS S3 bucket, and that website shall show one of the 3 words we have defined here in the array, and we want to randomly pick which one of these. How that works is we write an imperative program that through the execution actually defines a target state declaratively that then is handed off to a deployment engine that does the deployment for us. And the target state in these deployments is a directed acyclic graph where the nodes are resources and the arcs are dependencies between the resources that order the deployment. And for our small example, our small web page, this would be the target state. We have 3 nodes. We have the AWS S3 bucket. We have something that gives us a random integer. And then we have the index object that we put in the bucket and that we configure with this random integer. That's how we get the arcs. So how does the program that generates looks like? So this is now Pulumi TypeScript. For each resource type, we have a class, and we define a node in the target state by instantiating an object from the class. So what we do here in line 3 is we instantiate an object from the S3 bucket class to define that node. Similarly, we do that with a random integer. Here you can also now see when we call the constructor, we can give it the configuration of that resource. So in this case, we give it a minimum and a maximum value for the integer generator. And the same we do again for the bucket object, for the index. To get that node in the target state, we again instantiate an object of the resource classes type. What is missing now is still the arcs, the dependencies. There's 2 ways to define them. One is explicit by referencing an existing resource object in new objects on configuration, and we have that here with a bucket. So that's how we get the right arrow, not arrow. And the other way is doing it implicitly by having the object instantiated in a code block that depends on output configuration that is available on an object after deployment. And that's what I show you now here. So what we do in line 9 is we take our random number generator, the object RNG, and post-deployment, the randomly drawn number is available in the result property. And we register with this apply a callback that is executed on this post-deployment value. And because our bucket object is defined in that callback, we get this implicit dependency which is the left arc in our target state. So this is a regular imperative program that defines that target state. And we can hand that now to the Pulumi CLI, which executes that. This is how it looks like. Takes a bit, creates the resources, and eventually, ta-da, we get our website. Everything is fine and working. We did this exercise and didn't just click in the console because we want to do something, that is actually nicely defined and re-executable, right? Reproducibility is a big reason for infrastructure as code. So if we do it again, we expect that we wait again, roughly 10 seconds, it creates some objects, and then we hopefully get again our nice website. Not in this case. And this is particularly bad because some resources got created, some didn't. And I mean, it worked the first time. This seems to be even an error that doesn't only happen. This is an error that sometimes happens. So that is bad. So let's look at the error message. So what does it state? Cannot read properties of undefined, reading to lowercase in line 12. If we look at line 12, okay, we call to lowercase on what we get from the array. Words ID is undefined if we actually made an access out of bounds. So our array has 3 elements, so ID seems to be not 0, 1, or 2. So where does ID come from? It's the parameter in the apply callback, and that is the post-deployment value of our random number generator. So we have to look at the random number generator configuration, and we see we configured it from minimum 0 to maximum words length. Words length is 3. So we just did a misconfiguration here. That's the error. We set it to draw a number from 0 to 3, but 3 is an invalid value. We get the index out of bound problem here. So that was a bug. We fix it by adding the -1 here. And this is a bug, I mean, one-off bug or index out of bound bug. We know that from every software, yeah? Right? This is nothing special, but we also have it now in infrastructure as code programs. And in classical software, we would say, well, this is a common problem, but we have techniques for that. And one common technique, I would at least argue, is testing. So if we do testing for traditional software, we now have the same problems here. Let's do testing. And that's what we thought too. And started off with looking at which testing techniques are actually available for these kind of programs. And we found it's very similar to what you have for traditional software. We ended up getting a testing pyramid with end-to-end testing at the bottom, some intermediate steps of integration testing in between, and on the top we have unit tests. And unit tests are quick and can be frequently executed locally, and end-to-end testing is the slowest version. You saw even for this small program, it took already 10 seconds when we executed the CLI. If you have complex deployments like with databases, Kubernetes clusters, whatnot, a single execution easily takes minutes up to hours. In practice, that's really the case, up to hours. So as a developer, what you usually want, traditional software, and I would argue it's the same for infrastructure as code programs, that you find as many bugs as possible with unit testing. So you want to have unit tests to find bugs as early as possible, because these you can execute frequently and cheaply. So we thought, well, do infrastructure as code programmers actually do unit testing? And to answer that question, we had a look at all public Pulumi TypeScript, or generally all Pulumi programs you could find on GitHub. That was roughly 13,000. And then we tried to figure out which of them use unit testing. And we found out it's pretty much almost no one. So less than 1% actually had a single unit test implemented. Yeah. So even the ones that are mentioned here doesn't mean that they do proper unit testing. It just means that they have one unit test. So seems like there is an issue. There is a gap. But where does that come from? So, and to understand that more, let's perhaps look deeper into what is actually going on. How do these programs work? What do we have to do in unit testing? And if we look again at our example, we have that now here on the left side. What our program does in the regular execution is it integrates with the cloud. Yeah, because it shall, through the execution, deploy something in the cloud. And what actually happens in our concrete example is we first started off with generating an input configuration for the bucket, for the AWS S2 bucket. And then we called the resource constructor, and that sends the input configuration for that bucket to the cloud, and then the cloud deploys that bucket and returns the output configuration of that bucket. And this output configuration is then available on the bucket's object in the remainder of the program execution. And then the same happens for the random integer. We created an input configuration, sent it to the cloud deployed the random integer, and returned an output configuration that is available in the remainder of the program execution. And then the same happened again for the bucket object. Now, this is what happens if you really execute that. It integrates with the cloud, it heavily depends on it. That's the slow part. In unit testing, we want to get rid of the cloud. So we replace it with a mock. But the mock itself now has a role. Yeah? It plays the cloud in our tests. And let's make explicit what it actually has to do. The first thing is it has to return for us, for every input configuration that we give to it, a realistic output configuration. Why does it have to be realistic? Well, this output configuration can be accessed in the remainder of the program execution, so it's actually test input. So it's really crucial that this output configuration makes sense, because this is what we test our program on. So eventually, this mock is a test generator. The second thing that we most likely want to have is we also want to make sure that the input configurations we get are actually sensible. Do they make sense? So we want to have some validation logic. And in testing terms again, this also means that our mocks are test oracles. Yeah. So it's actually quite involved. Yeah. We have to mock, okay, that's one thing, but we have to implement good test generators in there and good test oracles. Okay, now we know that, let's do it. Let's go back to our example. So we start with a simple unit test. This unit test just configures now Pulumi's runtime to use a very simple mock whenever we define a resource. This mock is very simple. It just returns the empty state and doesn't do any input validation. In line 14, 15, we just execute the program and wait for its termination. So this is 16 lines now, as long as the program. However, if the program would grow, the test would stay as long. However, this unit test is useless. It's completely useless because we we only have one test in general that we can test with it, and that's the one where all output configurations are empty, because we always generate the empty state. And we also never validate any input configuration. So let's solve the first problem first. Let's make this a sensible test generator for our program. Yeah? So this is now a minimal extension to make this a sensible test generator. It only returns also now test output that is really used in the remainder of the program. If we really would like to generate complete output configurations, this would be even longer. But now we have a suitable test generator. But we're still missing input configuration testing. So to have input configuration validation, let's add more logic. And now this is also a beautiful test oracle. This is now a decent test, 50 lines for 14, 15 lines program. But I have bad news. If our program grows, this unit test is very likely to grow even faster. And it's also more or less, not that idiomatic, because it basically re-implements all logic that we have in the program, but in not so nice. And even worse, it re-implements logic that is actually not implemented by our program, but by the cloud or its providers. So obviously we have high coupling, we have a lot of code. This is just a lot of development effort and super slow. Yeah? So no wonder, at least from our conjecture, that nobody does that. So how do we get out of there? I mean, that's the problem. Let's get to the solution. And our solution is, let's automate. Let's try to automate as much of this as we can. And the conceptual framework that we came up for this is automated configuration testing. And what we do there is we have on our infrastructure as code program, and at the core we automatically mock all resource creations. And obviously, on a technical level, high level, this is very simple, but as I showed you already, this test generation and test oracle implementation, that's not trivial. And that's also why we don't do it in the framework. We have plugins for that. So we have a plugin interface for generators plugins, and the single task of these generators is to provide for every input configuration a suitable output configuration. And in these generators, the idea is to implement generalizable, reusable test generation strategies, such that you can once implement such a plugin and then reuse it across different programs. Even further, you can move the effort from the program development or from a company towards the community. The community once comes up with good plugins, and then everyone can use them for free. And similar, we also have a plugin interface for oracles, where the idea is that these are plugins that validate input configurations. Again, the idea is the community comes up with great oracles that are reusable and generalizable, and then everyone can use them for free. And at this degree of automation, we have fully automated test execution without writing one line of code. Now you can write your new infrastructure as code program, and without writing a single line of testing code, you can test it on many, many different configurations through reusable plugins that the community provided for you. This gives you a head start for free, basically. Still, there may be properties, of course, where you want to leverage application-specific knowledge that you have, where you want to narrow down test generation or want to have a bit more precise oracles. And also that we want to make easier, and for that we provide inline specifications that allow to use very, very small annotations to have application-specific generation and oracles in there. So this is a small example snippet where in red we have these annotations. So in line 9, for example, we annotated that the output from our random number generator should be generated with a ps.integer RNG range. That's an arbitrary that we configured, where we basically override the test generation of our generalized plugin. In lines 15 and 16, that's an example of an annotation for an additional oracle check. So this is basically an additional check that looks whether the content that we deploy on the index page is empty, or basically it ensures that it's non-empty. Yeah. Okay, so this is the overall framework. The idea is to move the hard things into generalizable plugins that the community can maintain, share, and ideate on. and then have a framework that puts all of this together and allows you to test quickly many different configurations without writing a single line of code. More concretely, we implemented this for Pulumi TypeScript in a tool that we call ProTI. We have a website for that. It's public on GitHub and on NPM. The QR and link for that is on the last slide of this talk. But what technically ProTI is, it is a set of plugins for Jest, which is a popular JavaScript, TypeScript testing framework that originated at Facebook. And basically ProTI is a runner and a test runner and a reporter for that. And the core of ProTI itself reuses a library called FastCheck, which is arguably the most popular property-based testing framework that is currently available for JavaScript, TypeScript. That's the basic framework. Of course, where we really get like traction, where this becomes really useful is the plugins. And we have here first plugins now that are type-based. What we do there is we use type schema descriptions that are available by default for all Pulumi descriptions. And we use these type descriptions to randomly generate reasonable output configurations. And our input validation, our Oracle currently checks all input configurations that for type compliance. Of course, this is very simple, but it seems to be already very effective. We found it to be effective already. But this is exactly where we have now our future work. Yeah, so having more sophisticated oracles that implement better models and using more sophisticated test generation strategies that use techniques like symbolic execution, concolic execution for better test generation and guidance. That is where we want to put future work into, and hopefully also hope for the community to chime in. Yeah. We evaluated ProTI so far for various questions. Very briefly, we evaluated it on various variations of the example program that I showed you, and through that we could find that ProTI can find bugs reliably, even in cases where the bug sometimes shows up, sometimes doesn't. We ran ProTI on all the Pulumi TypeScript programs we found in our GitHub study. That was 6,000. On roughly 40% of them, we actually could execute it without doing any change or trying to understand the program. So this shows ProTI can be thrown at programs in the wild. And if you put a bit thought into it, most probably also in a lot of the other 60%, it didn't run out of without putting too much thought into it. ProTI typically needs for a single test execution something between 100 and 300 milliseconds. So it's arguably pretty fast. You can run it in tens, 100 times on a program within a minute. That's no problem in practice. And we also had various tries to implement small plugins that reuse existing tools. So we had a very naive integration with the Radamsa fuzzer and with the Daikin invariant detector that showed, yeah, our plugin interface is powerful enough to use existing techniques as plugin in our approach. With this, I'm at the end of my talk. I provided to you a little example of programming languages infrastructure as code. Then I hopefully convinced you that testing these programs is a bit different and especially more effortful than for traditional software. That's why most likely nobody does it. Then I showed you our conceptual solution for that, a framework called automated configuration testing, which automates all this effortful mocking and moves the hard parts of it, the test generator and the Oracle implementation, from individual programs towards the community, leveraging reuse. And our implementation for it, which is ProTI for Pulumi TypeScript. There's the QR in the website if you're interested. And at the end, I quickly summarize the evaluations we did so far. Thanks for your kind attention and looking forward to your questions.
Thanks a lot, Daniel. Any question? Yes, Marcus.
So if you're now using the Pulumi schema, I'm not entirely familiar how they're represented, but is it then still really tied to TypeScript, or could you very easily also support the other languages?
So the schema is language agnostic. Mm-hmm. Exactly. So that's the same for all languages Pulumi provides. So conceptually, we could provide any language our actual implementation for Jest is very bound to TypeScript because it's written in TypeScript, it's running in Node, but you could easily re-implement it conceptually for Python or for Go or whatnot. Okay. So the approach is language agnostic, the implementation is specific, but the idea with the Pulumi types is also language agnostic. That would work for Python, Go the same way.
Yeah. So I'm not sure why it's then tied to TypeScript. The language in which it's implemented shouldn't matter, right? Like if you have the Pulumi evaluation, so I generate, because under the hood, Pulumi is fully data-driven and declarative, right? So you could just interface at that level, or am I missing something?
Yes and no.
Okay.
So it's, I think practically from an implementation point of view, we mock directly in the program. So we mock still in TypeScript. You would be right if we would mock in the deployment engine, which would be a step later. So it means, so practically what Pulumi does is when you instantiate an object, there is a remote procedure call. It's actually gRPC to their deployment engine, which is implemented in Go, and that does then the interaction with the cloud. And we don't mock in the deployment engine, we mock before that RPC. That's why our implementation couldn't be reused with Python at the moment.
Yeah. All right.
Just hacking the question, but follow-up question, why don't you mock at the deployment engine level?
For performance reasons. gRPC is fast, but not having it is faster.
Fair enough. I don't remember Alex.
It's very similar to what we are doing and what we're going to talk about. But as far as I understand, most of the oracles will be able to catch only intentless, or will be able to perform only intentless validations. I mean, there should be a clear distinction of whether this particular state is invalid. What if there is a state among all valid states which is not valid for this particular developer? Do you know how your framework can cover this use case? For example, I will give you an example. I want to deploy a container, and I want my application to have enough memory in this container and some overhead. But this overhead cannot be defined in my language because there is no place for this language, for this thing to be defined.
I'm not 100% sure whether I got the question, but it sounds to me very similar to a general problem you have with policies. And actually one idea that is very close now is because policies are available for Pulumi, for example. They just released, again, new sets of best practices as policies. And one idea is to also implement an oracle that actually uses these policies as a model. And then you could implement an oracle plugin that uses your own policies, and perhaps you have a policy implemented that says, well, for this environment, we have a bit more leeway, but in general, we want to have only up to 2 gigabytes of memory. So that would be possible, but eventually you would have a parameterized oracle, in this case, parameterized by a policy.
Nice talk. Oh, I just have one clarification question. So you mentioned that you ran ProTI on a lot of real-world code. What does that mean exactly? Because there were some repositories, and then it turned out that only 1% of them had a unit test. So did you automatically create mocks for those unit tests, or did you automatically generate new assert statements? Or
very good question. So we automatically mock every resource creation. So that means we don't need any existing testing code to find out what we mock. How this is implemented generally, Pulumi, we have a very simple mechanism to automatically mock all resource creations independent of whether there was tests or not. Assertion statements, so that's the question for the oracles. So the oracle that we applied was our type-based oracle. So we basically checked, do all configurations that are actually configured for resources comply with the types that are expected. So this is only a rough approximation because these types are very, very coarse, right? There's strings and numbers, but formatted strings, or whether the number is now an integer or a float, to that precision we don't get. So that's also why I'm a bit defensive in saying we could show these programs are correct or not. What this experiment showed is you can use ProTI with that, with these programs out of the box. When ProTI shows a bug, it's very likely that it's an issue. When ProTI doesn't show a bug, it still, I mean, eventually it's also testing, it still doesn't say that the program is correct. You may need better oracles.
How often did it say it was a bug? How many?
It was roughly a third of the 40% that had found a bug with that simple oracle already. Yeah.
That doesn't surprise me.
You've seen things.
I've seen things, yeah.
Any more?
Very good.